Black holes are some of the most extreme and fascinating objects in the universe. They are not holes in space, and they are not cosmic monsters that suck everything in. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it passes a boundary known as the event horizon. Black holes exist because of Einstein's general theory of relativity. According to this theory, mass bends space-time, and if enough mass is compressed into a small enough volume, space-time curves so extremely that all paths lead inward. At that point, escape becomes impossible. Most black holes form from the death of massive stars. When a very large star runs out of nuclear fuel, the outward pressure created by fusion disappears. Gravity then causes the core of the star to collapse inward. If the remaining core is massive enough, not even neutron pressure can stop the collapse. The result is a black hole. This process often happens during a supernova explosion, where the outer layers of the star are blown into space while the core collapses. There are several types of black holes. The most common are stellar mass black holes, which typically have between about 3 and 100 times the mass of the Sun. These black holes are scattered throughout galaxies, including our own Milky Way. Another type is supermassive black holes. These have masses ranging from millions to billions of times the mass of the Sun and are found at the centers of almost all large galaxies. Our galaxy contains one with a mass of about 4 million suns. There are also intermediate mass black holes, which fall between stellar and supermassive black holes. Evidence for their existence has grown in recent years, though they are rarer and harder to detect. Finally, there are primordial black holes, which are hypothetical objects that may have formed shortly after the Big Bang. As of now, none have been confirmed. A black hole has several important regions. The event horizon is the most well-known. It marks the point of no return. Once something crosses this boundary, it cannot escape, no matter how fast it moves. The event horizon is not a solid surface. It is simply a boundary in space-time. At the center of a black hole lies what is called a singularity. According to current theory, this is a point of infinite density, where the laws of physics break down. Scientists do not know whether singularities truly exist as infinite points, or whether a future theory of quantum gravity will describe them differently. Around many black holes is an accretion disk. This is made of gas, dust, and other matter spiraling inward. Friction and gravitational forces heat this material to extremely high temperatures, causing it to emit intense radiation, especially X-rays. This radiation is one of the primary ways astronomers detect black holes. Some black holes also produce powerful jets of particles that shoot out along their rotational axes at nearly the speed of light. These jets are driven by strong magnetic fields and the black hole's rotation. One of the strangest effects near a black hole is time dilation. Gravity affects time itself. Near a black hole, time passes more slowly compared to regions far away. To a distant observer, an object falling toward the event horizon appears to slow down and never quite cross it. To the object falling in, however, time feels normal, and it crosses the event horizon in a finite amount of time. This effect is not just theoretical. Gravitational time dilation has been measured and confirmed in weaker gravitational fields, such as near Earth. Another dramatic effect is called spaghettification. This happens because gravity is much stronger closer to the black hole than it is farther away. The difference in gravitational pull stretches objects lengthwise and compresses them sideways. For stellar mass black holes, this stretching would be fatal long before reaching the event horizon. For supermassive black holes, the tidal forces at the horizon are weaker, meaning an astronaut could theoretically cross the event horizon without immediately being torn apart, although survival would still be impossible shortly afterward. Black holes cannot be seen directly because they emit no light. Instead, astronomers detect them by observing their effects on nearby matter and light. They measure the motion of stars orbiting invisible massive objects, detect X-rays from accretion disks, observe gravitational lensing where light is bent around massive objects, and record gravitational waves produced when black holes collide and merge. Astronomers have also directly imaged the shadow of a black hole, which is the dark region caused by light being captured by the event horizon. These observations match the predictions of general relativity extremely well. A common misconception is that black holes act like giant vacuum cleaners. This is not true. From far away, a black hole's gravitational pull is no different from that of any other object with the same mass. If the sun were suddenly replaced by a black hole of the same mass, Earth's orbit would remain almost exactly the same. Black holes only become dangerous when something gets very close to them. Black holes are also not completely eternal. According to theory, they slowly lose mass through a process called Hawking radiation. This radiation arises from quantum effects near the event horizon. Over extremely long periods of time, a black hole can evaporate entirely. However, this process is incredibly slow. A black hole with the mass of the sun would take far longer than the current age of the universe to evaporate. Hawking radiation has not yet been directly observed, but it is widely accepted as a strong theoretical prediction. Despite everything we know, black holes remain deeply mysterious. Scientists do not know what truly happens inside the event horizon. It is unclear how gravity and quantum mechanics work together at the singularity. There is also an ongoing debate about whether information that falls into a black hole is destroyed or somehow preserved. These questions are at the forefront of modern physics. Black holes are not just strange cosmic objects. They play a crucial role in the universe. Supermassive black holes influence the formation and evolution of galaxies. They help regulate star formation and shape the large-scale structure of the cosmos. By studying black holes, scientists test the limits of our understanding of space, time, and reality itself. In many ways, black holes mark the edge of human knowledge. They are places where our current theories work remarkably well, and also places where they clearly fail. Understanding black holes is not just about understanding what happens when gravity becomes extreme. It is about understanding how the universe truly works at its deepest level.